microscopy. As I have already discussed in the last class about the confocal microscopy, it deals with the excitation and emission of the atoms. Okay. It deals with the excitation and emission of the atoms. Now, coming to the confocal microscopy, it is the modified version of fluorescence microscopy. Okay. Confocal microscopy is the modified version of the fluorescence microscopy. Now, what is fluorescence microscopy? I will just give a glance and clear important aspects regarding the fluorescence microscopy so that you will be understand the confocal microscopy. Now, what is fluorescence? See, whenever a light falls here, okay, whenever a light falls on an atom, what will happen? The electrons which are present in here will jump to the higher excited state. The electrons which are present here will jump to the higher excited state. Okay. Now, what will happen after jumping? They will come back to its ground state. Okay. The electrons present in their ground state will jump to the excited state. After that, they will come down. While coming down, they will emit some amount of energy. It is called as fluorescence. Okay. While coming down, they will emit some amount of energy. It is called as fluorescence. But what will happen? The energy, the atom, the electron is taking is more compared to the energy it is leaving. Why? It is because of the vibrational relaxation. This point I haven't told yesterday. The main reason is vibrational relaxation. Okay, because of the vibration relaxation, some amount of heat is dissipated, means some amount of heat is lost. That's why the excitation energy, the light which comes and hits the electron, is more than the energy which is emitted. As we all already know that energy is inversely proportional to wavelength. So here the energy is more, means the wavelength is less. Here the energy is less, but the wavelength is more, and it is called as fluorescence. Okay, because energy is emitted in the form of radiation, that is light, which we can see in the form of fluorescence. Now, what is phosphorescence? Phosphorus is also a same, one and same, but the main difference between fluorescence and phosphorescence is the fluorescence is instantaneous, means you are uh, giving light to a object, you are giving light to a specimen. At that time only, in nanosecond to microsecond second, instantaneously, suddenly, you will see the fluorescence, you will see the color. Okay. But what is phosphorescence? Whenever, if phosphorescence is like radium, you will give light to the radium, but it will give the color after it can maintain the color till the long time. It is called as phosphorescence. Okay, because it may be referred milliseconds to minutes. If you're giving a light to an object now, but it is able to glow after 10 minutes also, it is called as fluorescence. The fluorescence is instantaneous, immediate, but the phosphorescence is it can maintain up to some time. That is the difference between fluorescence and phosphorescence. Hmm. As I've already said that the energy of the excitation will be more, means the wavelength is less. Here, see the excitation is in the form of blue color here. The energy is more, the wavelength is less here. But the emission, the energy is less, but the wavelength is more. If you can see it in the clearly here. So, but the difference between this excitation and emission, it's called a Stokes shift. Okay, the difference between excitation and emission is called Stokes shift. Now, see, there are some molecules which are having tyrosine, tryptophan, reduced NADH, serotonin, and FAD nucleotides. They will have intrinsic fluorescence. Means there is no need to attach a dye. There is no need to give any chemical. There is no need to give any external factors, any extrinsic factors to make it glow, to make it give color. That's why these uh, elements are called as intrinsic fluorescence giving elements. Okay, these will have a intrinsic fluorescence of themselves. Okay. Mm. Uh, Bhavika Jain, can you please turn off your mic, please? Yeah, thank you. So, so, uh, what will be there as a light source? Okay, I've already talked in the last class about the fluorescence microscopy. It will be having mercury arc, xenon arc, metal halide lamp, and the filters. There are excitation filters, diachronic filter. Why diachronic or dichromatic mirrors? Di means two, and chromatic means colors. It will be able to filter two colors, one with excitation color and one with emission color. Okay, that's why it is called as dichromatic filter. And there are two other filters present, which is there for specifically excitation, and one which is there for specifically emission. Okay, and what are the fluorescence dyes and tags? As we have already said, only these type of molecules will have intrinsic fluorescence in them, and there are some molecules or there are proteins which are not having the intrinsic fluorescence. They cannot give color by themselves. So you have to add some dyes, some tags. So what will be the dyes? They may be FITC, Psi2, Psi3, Psi5, Texas Red, tetramethyl rhodamine. These are some dyes by which you can uh, give color to your specimen. Okay, by which you can give color to your object. For nuclear dyes, if you are having DNA, if you are having RNA, okay, if you are having DNA, it should be given color by ETBR. ETBR means ethidium bromine. Only ethidium bromine can give the color to DNA. Okay, not uh, not this Texas Red or not this FITC. Only ETBR can give for nuclear dye. And in the same way, red and orange can give color to DNA. DAPI can give color to DNA. Only these things can give color to DNA, not this dyes which we are using. Okay, not this fluorescent tags or dyes which are using here, but these dyes. Even for PCR, polymerase chain reaction, we will use ethidium bromide to visualize the DNA, to visualize the DNA. So, but for nuclear dyes, what you'll use? We will use ETBR, red and orange, and DAPI. And for CA+2 indicators, we will use GFP, yellow-green fluorescence, and cyan-green fluorescence. And for mitochondria, if you want to visualize mitochondria, how may see there may vary 1 to million mitochondria in one cell. You want to count how many mitochondria are there? Is there are 10 mitochondria or 50 mitochondria? How you will know? You can label the mitochondria with rhodamine 1 to 3, rhodamine 1 to 3 dye. So you can know how many mitochondria are present in the cell. Okay. Now, what is this trichronic or dichromatic mirror? See, this is the light. This is the light. It may be mercury light or xenon light, as I have said here. After that, this light will hit this dichromatic mirror. What is this dichromatic mirror will do? It will have the specific selectivity for two different wavelengths. One is for excitation wavelength and one is for emission wavelength. And this dichronic mirror can reflect at the 45-degree angle. See, if you see the angle of this mirror, it is 45-degree. It will pass this excitation wavelength of light, and after that it will hit the specimen, and from the specimen it is going, and it is passing to diachronic mirror, and it is giving to emission filter here. Here we can see the specimen. Okay, this is the see, you can see the setup also here. How is the setup? There are so many lights here: green light, blue light, red light. But only blue wavelength light is passed here. See, but only the blue wavelength of light is passed here because of the excitation filter. And the, after taking the low wavelength of light, it will emit the high wavelength of light. Why? Because here energy is more, here energy is less. So wavelength is less, a wavelength is less here and wavelength is more here. So while the specimen will emit the green light, it will pass through this diachronic mirror, and after that it will go to emission filter here. So it is called as epifluorescence microscopy. Why it is called as epifluorescence microscopy? Because the incident light and the emitted light, both are upwards to the specimen. Both the both the emitted light and the excited light, both are there top upside to the specimen. That's why it is called as epifluorescence microscopy. Okay. Now, what is the application of this fluorescence microscopy? See, either you can see the intracellular distribution of macromolecules. E- Either you can see the intracellular distribution of macromolecules, like where are the proteins are there, where is the DNA, where are the lipids in the inside the cell. If you want to know where is your um mitochondrial protein is present, RON6. So where what you'll do, you will label the RON6 and you will know where is the distribution of that protein. From the mitochondria, is it going to Golgi complex, or from mitochondria it is going to endoplasmic reticulum. So you will determine the intracellular distribution of macromolecules. Or you can study the intracellular dynamics of macromolecules. It is called FRET. Intracellular dynamics means, for example, uh, there is a movement of one transcription factor. Okay, there is a transcription factor is protein. It will go and bind to your DNA. You can know the dynamics of that, and also you can know the dynamics of your organelles. Organelles like with which are there are so many organelles like membraneless organelles are also there, membrane organelles are also there. Mitochondria will also move. Cytoskeleton elements will make some proteins to move. All this be studied by Fred. And what is Fred? Okay, it is the resonance emission. It deals with the resonance. See, one if one dye particle is going and binding to your specimen, it will make the surrounding dyes also to make give color. Why? Because it is passing the resonance energy. Okay, that is why it is called as FRET, resonance energy. Okay, and you can find out the endocytosis, exocytosis, protein sorting, signal translation, cytoskeleton dynamics, and you can also see the immunofluorescence. What is the immunofluorescence here? Immuno, it is the antigen and antibody complex. Whenever there is an antibody which is conjugated with the antigen, whenever this antibody conjugated with the it was a mistake. Whenever an antibody is conjugated with the fluorescent dye, what will happen if this antibody will recognize the antigen in the slide and it will come and attach it to it? The this will give color. The fluorescence dye will give color, so you can identify the antibody that is attached to the antigen by the fluorescence of this dye which is conjugated to antibody. Like, and you can do fish and frap also. Frap is the fluorescence recovery after photo bleaching, and fish fish we will do it is the in situ hybridization. For example, you are having chromosomes. The chromosomes can undergo translocation. The chromosomes can undergo mitosis, meiosis. At that time, what are the chromosomal aberrations? Means, what are the chromosomal problems? It may be undergo 21 down syndrome or Turner syndrome. How will you know there's a possibility? It is because of the fish. You can understand the genetic disorders. Okay, it's the chromosomal aberrations, fluorescence in situ hybridization. And now, what is that making difference from the fluorescence microscopy? Okay, the confocal microscopy is same as fluorescence microscopy, but it is a modified version. How this confocal microscopy is the modified version of the fluorescence microscopy? It is because of there are two sets of pinhole apertures. What are there? There are two sets of pinhole apertures in the confocal microscopy. This is the basic and fundamental difference between the fluorescence and confocal microscopy, which may be asked in any exam. This question, I think it came in a bark or something in the last 2 years or like that. So what is the fundamental difference from fluorescence and confocal microscopy? It is the use of two set of pinhole apertures. Okay, what does this pinhole apertures do? They will focus the light in one plane and not allow the light which is out of plane. It is giving the specificity. It is focusing. That's why the name is called confocal, which is giving focus microscopy. Okay. Now, what will happen here? The resolution is enhanced. The image will be sharp. Okay. In confocal microscopy, the light will be focused at one plane, and another plane, the light is which is out of plane, it is not allowed, and there is an enhancement in the resolution, and the image which is formed, it is very sharp. Okay. Now, coming here, what is happening? See, as I've already said, there are two sets of pinhole apertures. No, this pinhole apertures is the heart of confocal microscopy. It is very important because it is very important. How it is important, you will see here now. Okay, see, whenever a light is passing through this pinhole, okay, whenever the light is passing through this pinhole, what is may happen? The light, see, there is a green light, red light, and this blue light also. But because of presence of this pinhole, only the green light is passing here. See, only the green light is passing here. So you can fix the focus point here. Because of the pinhole, you can fix the focus point at what point exactly you want to see the specimen. See, uh, if I keep this pinhole little down, see, from here, what I'm doing, I'm keeping the pinhole little down. So what I'll do, I can see the lowest part of the specimen. I can focus on the lowest part of the specimen, and I can see the what is there here in the specimen. Okay, so the pinhole we can move up and down. We can focus on which part we want to see exactly, and which focal plane you want to see exactly, and you can see at the particular specimen a particular focal point. That is the main use of the pinhole. For because of doing this, what is happening? The resolution of your specimen, the clarity of your specimen is increasing. See, okay, see, there are two pinholes here. Okay, this is a laser. It is hitting the object. Where it is hitting? It is exacting at the specific point, 3D focal point. After that, what will happen? The electrons which are present here will excite. Okay, and after they emit the light, what is happening? It is going to second pinhole. The emission is, and it is seen by the detector here. Okay, sorry if I am fast. What is happening here? The laser is hitting the mirror, and it is hitting the specimen, and the atoms present here will get excited. Okay, after and they'll get excited and go to upper state, and when they're coming down, the energy is released in the form of emission, in the form of light, and it will give color. How it will give color? Because the energy here is more, energy here is less. Energy here is less means the wavelength is more here, and it will travel to the pinhole, and it will emit here. Okay, and the emission is seen in the detector here. Now, see, what is the main difference between fluorescence and confocal? See, the resolution here is very poor. Why? Because it is not focusing on the particular 3D focal point. That's why in fluorescence microscopy, the resolution is not sharp. The resolution is not clear. But when coming to the confocal microscopy, if you can see here, the resolution is very clear. You can see the every cell. See, you can see every cell. Okay, and you can see each and every color, see green color, red color, because that your specimen is having. So that is the resolution is the main difference because of the presence of two pinholes in the confocal microscopy. Hmm. Applications of, as I already said, you can do the fish detection. And one more important, see, this is the important question, by which, using which microscopy you can see the colocalization of proteins. There are so many microscopy, no? Phase contrast, phase contrast microscopy, bright field microscopy, electronic microscopy. But if the question comes like in any exam, if the comes like, what is used for the co-localization of the protein, which microscope is used for the co-localization of proteins? It is the which microscopy? It is the confocal microscopy. What happens in the confocal microscopy? See, if in the same place, Okay, if in the same place overlapping one another means here see I'll draw this. See it. See now what is happening here. See what is happening here in the same plane. Okay, in the same plane how many colors are there? There are three colors: a red color, yellow color, and purple color. But what we will see, if you are you can see only red color from the above, no? But by using this by using this confocal microscopy, you can see the co-localization of proteins. Means in the same point, in the same focal point, if there are three colors, what you can do, you can give color of you can give color to, for example, see here, there is this is the actin, this is vinculin, and these are normal teher ovarian cells. These three are present in the same plane. See, there are see three, these three, like these three lines are there, there are three are present in the same plane. If you use normal fluorescence microscopy, you can't maybe not find the difference, but you use the confocal microscopy, you can see the co-localization. They are localized together. That is the meaning of the co-localization. If you see here, one is having red color, but one is having a green color, but these are having some different color. But when you see this xyz dimension along with the time, multiple colors can be seen. See, this everything is in one image only. This is the one image, but you can see three different colors in it. This is for actin, this is vinculum, these are tear ovarian cells. These three images you can be seeing with the single image taken by the confocal microscopy. That is the important aspect of the confocal microscopy. With a single image, you can see the co-localization of proteins, which are stacked one above the other like this, but it is differentiated as A, B, C because of the confocal microscopy. It is the 5D view. Why 5D view? Because of this. You can see the entire XYZ axis like this, XYZ axis, and you can see the 3D view also. You can see the 5D view also. You can rotate these cells. You can see what is the behind, what is the front, what is sides. You can see in the confocal microscopy. Okay, and optical sections. If you are having a tissue section, okay, you will cut the tissue and put it on a slide. And if you see in the confocal microscopy, you can see the 3D view. Okay, and composite view. Composite the entire view. Okay, this is all about the uh, this is all about the confocal microscopy. If you are having any doubts regarding this, please feel free to ask the questions. Okay, if you are having any doubt or any question, you can ask the question.